for prediction problem. Images are the data for computer vision. We will not talk about video generally because video we try to think of it as frames per second, which is a frame is still an image. So when any algorithm processes video, it actually processes it at frame level. At the max, what it does is it remembers what happened in the previous frame and relates it with the current frame. So at which point it doesn't really become so at the time, it becomes more like a time series problem rather than a computer vision problem. We will not talk majorly about videos in this session. We will talk about images. The idea being videos are just images with a lot of frames per second. So a frame is an image, and if you understand what happens at a frame level, we will understand what happens at the video level. Okay, you want the email, right? Okay, sorry. So I've given all my email addresses here. Okay. So an image is basically brightness level at a pixel level, brightness at every pixel, right? So a completely dark pixel where there is no information is going to be dark, zero, and a very at the very maximum at its maximum brightness, a pixel is going to have a value of 255. Assuming that it's 2 power 8, it's 8-bit and all that, we'll not go there. But generally, the pixel value ranges from 0 to 255, right? And the individual colors which we see are basically R, G, and B. A black and white image or a grayscale image is basically doesn't have any color information. So at every pixel, it's going to have at a pixel 0 to 255 level. Whereas a color image is going to be a combination of red, green, and blue channel. So that's going to be a red channel, a green channel, and a blue channel. Um, it's going to be three-dimensional. So a red is going to have at its maximum brightness 255. Again, the darkest being black, brightest being as red as it can get. For green, similarly, black to as green as it can get, and blue 0 to 255. So if you take an image as a consider image as a data, the pixel value is going to be the data that's going to go as data into the image, right? Unlike text, which we discussed yesterday, images are fairly simple to feed into neural network. And generally, the yellow, cyan, magenta, different colors that we see are different combinations of red and green. For us to really understand this at okay, okay, so this is the image. It's a very small image. Um, as you can see here, I'm pointing at a pixel and the brightness level at that particular pixel, you can see in this part, right? So if I point my cursor at a very bright white part of the image, you see a value 256. So that's how bright, that's as bright as it can get. If I go to some of these black regions, you can see that the value actually reduces. Okay. The value reduces. It's 24, 25, very, very less numbers. It's 32 here. And anything in between, there's a grayish kind of area, and the pixel value there is 191. This is a fairly bright area, it's 238. So that's what images really are. Okay. Um, I'm sure that this is common knowledge, but I just thought I can give a quick intro. Can I just move on from this point? Or is there any questions, anything that you want clarified here? All good?
Yes.
Okay. Okay, and I'm sure you would have seen this in Microsoft, like PowerPoint, wherever when you want to fill colors. If I keep red and green at 255, 255 and keep the blue at 0, I get yellow, right? If I get green and blue at 255, 255, keep red at 0, I get cyan. And white is basically a combination of all three at maximum. And black is basically 0, 0, 0. So whatever we saw for the grayscale image pretty much works for in color image, which we are going to call RGB image from now on. So at each pixel is going to be represented by three numbers. The first number, the red value at that pixel. The second number is the green value at the pixel. Third value is the blueness in that particular picture in that pixel, right? So a 0, 0, 0 is going to be complete dark. 255, 255, 255 is going to be full white. And different combinations of these numbers is going to give us the different colors that we can actually see. And that's going to be the food or the data for computer vision programs. And to be honest, what we see is actually a very small part of the bigger electromagnetic spectrum. But images from the other part of the spectrum and from other sources can also be useful as far as computer vision is concerned. But majorly, all our images are going to come from this very small part of the electromagnetic spectrum. Other sources of images, we can have infrared images, X-ray images, right? So when we say infrared, the heat capture and all that, those are pseudo color coded, right? We have a sensor which actually is sensitive to receiving those signals. It converts that into some sort of a pseudo color and it gives us the resulting image, right? Similarly for X-ray also. Other image sources, there is ultrasound. Again, sound waves are converted to images, and sonar again is converted to images. But the concept is basically the same. That's going to be RGB. Although the source is a sound-based system, it is converted to images, and that's what computer vision is going to use. For a lot of computer vision problems, we are going to have three types of images: a binary image, grayscale image, and color image. Binary image is basically made up of zeros and ones. There is no in between value. So every point in a pixel is either 0 or it's 255. So every point in the in the image is either 0 or 255. That is a binary image. Grayscale image 0, 255, and everything in between. As I said, color image is basically at every pixel value, there are going to be three numbers represented by the redness, greenness, and blueness. One small caveat I want to discuss before we go further is, of course, when you first actually look at these three images, it would actually look like binary images are basically not so useful. And as you can see here, this is a very high resolution, very nice image. Color images have the maximum information. That's what this slide would say. But think of a problem where I want to identify a letter. Okay. Um, I want to, let us say, identify what is there inside this. All these three, they have the same letter with redundant color information. Here, basically, the color is not that much useful if my problem is identifying the letter. Okay. If I'm going to send this or this or this into a network, a neural network, let's say the size of the image is probably 10 by 10 pixels. So that it has to process 100 pixels into three, red, green, blue. So 300 input features are going to go into the neural network, right? But if I actually convert that into a binary image, right, make it like this or like this, I can still do the letter identification task, but my input features is only 100, 10 by 10, and no values in between. So it's either zeros or ones, which makes the job of the neural network very easy, right? So although RGB images are the best that we can get, when it comes to business problems, we should always think if it's worthwhile to retain an RGB image as RGB image. Okay, that's one of the very basic things that we want to think about when we solve a computer vision problem. Any questions still here?
Yes. The option in the middle with the red letter A
Uh-huh.
and blue background, if I were to convert that to a black and white scale, wouldn't it all be black? Because it's
Um,
well, no, wouldn't they all be white? Either way, the
yeah,
blue and the red is like a very strong blue and a very strong red. So how will it know?
yeah,
We'd be happy to do something else other than just the strength
correct.
of the color to make the decision.
Correct. I agree with the premise. There are ways to convert an image into I can basically do a background foreground kind of a segmentation, and even if the foreground is like consistently 10 pixels more than the background, we can actually come up with an algorithm and we can separate the foreground and background, which is still computationally efficient than sending a full RGB image into an neural network. So yeah, we have to do something which will convert this into binary, but converting into binary is possible actually. Great question. I hope I answered your question.
Yes, yes.
Okay. Okay. So of course this is pseudo color coded. If I take an color image and break it down into its R component, which only the red channel, the green channel, and the blue channel, this is pseudo color coded, but essentially we can actually do that, right? So if my original image is 512 rows and 512 columns, So 512 rows and 512 columns and three channels. So it's a three-dimensional image. I can actually break it down into 512, 512, 512, 512, and 512, 512, which is the RGB complement of the image. Mostly that's what a neural network is going to get. Okay. To extend Eldad's concern, there's a whole thing called image processing and then a whole thing called computer vision. Sometimes they overlap, sometimes they work with each other. But basically, image processing is creating probably a new image from an existing one by modifying certain aspects of it, by modifying the contrast or by doing a foreground background segmentation, and that's something I'm doing with an existing image to come up with a new image. That is image processing, and in the strictest of sense, we cannot really consider that computer vision if it's going to be driven by a particular set of rules or algorithm, right? Like for example, removing the noise, normalizing brightness or color component of an image, converting a black and white image into a color image, a grayscale image into a color image. So all these things, um, they don't really understand the contents of the image, but they work with image and it kind of gives us a new image. So image processing and computer vision are overlapping, related, but also slightly different in terms of what we want to achieve through the process. Okay. So in computer vision, basically we want to see and understand the image. Like the same denoising, if I'm going to tell an algorithm to just denoise the image, right? It does so because it sees the noise in the image, it understands the task, and it implements a denoising algorithm, and it does that. So in that sense, it's computer vision. But in plain image processing, I'm going to define the rules of no denoising, and the algorithm is just going to implement it. Okay, so that is kind of image processing. And computer vision is basically further steps more than that, right? Where the algorithm basically understands the image, like the example that I gave yesterday, where it was able to make sense of the context and everything in the image before you without even be asking for it. Any questions here? Are you guys too distracted by the assignment? Are you working on it on the side? Because that happens. That's why I usually give the assignments, all these discussions at the end of the class. Because if I do it at the start of the class, it's very distracting. I've seen it in colleges. I've seen it in all different scenarios. I
I guess you're right.
know, I know. Usually, I make these announcements. I reserve the last 15 minutes for these announcements, actually. Uh, but today, for some reason, I started off with that.
I think if you relax the first come first served category as the criterion, it'll ease us a bit.
Okay, so that's what is driving the distraction.
Yes.
Okay, don't worry about that. Okay. Um, I mean, I can relax it, but the problem is everyone will end up doing the same thing.
I
Let's
think
let's uh, let's come back to the assignment for a few minutes. Please pay attention here.
yes.
The other alternate is I can randomly assign algorithms to each one, and I can just say no, do this.
So that's what I was
I'm
going to suggest. Run a randomizer script and just assign algorithms to each.
exactly
Yeah, that's the
that's
best
exactly
one.
Yeah.
okay because I don't want a distracted session. And I want peace back in the session. So it's just 7 algorithms, right? But
Yeah, sure.
so what I will do is there are 7 or 8 groups. So I just need to do 7 or 8, pick 7 or 8 algorithms and assign. What I can do is I can give, since there are 14 algorithms totally, I can give a choice. I'll give you two and you can pick one and you can just present that. So it will
Professor,
still be yours.
yeah, group 5 we have chosen VGG.
Okay, VGG is probably the easiest, right?
The easiness, does it impact on the evaluation, Professor?
Uh, Not really.
Okay.
Not really. As long as you can defend it well. So group one has already presented Llama.
Yeah, group 6 goes for Gemini, Professor.
Okay, group six is Gemini. Okay.
Presentation, what exactly are you expecting, sir? What kind of details you want to have into it?
Okay. So the presentation should basically include why that this thing is important, or why that architecture is important, what it brought to the table, what did not exist before that, and how it changed the field, and some general idea of what the architecture is about, like how many parameters, how the training is happening, what is one particular problem that it is trying to solve.
Professor, if the complexity plays a role, then we would move to BERT.
Give me 1 minute. I was opening my system.
Group
But,
3 was
but
paying attention to the class.
Might
What's
be
that?
as you go. Might be as you guided, you can randomly assign. Then it is easier for us to also focus and proceed as your it's been given. So whatever is been
Yeah.
given, it's fine. We can put our effort on that and we can shine on that. So it's for learning, is it? So yeah.
So what I can do is I can consider your whatever you have said now, because I don't want a distracted session really. Uh, if you can, and some of you have given your preference, I can consider the preference, but I'm not saying that I can't guarantee that I'll give it. I'll give the same this thing to you. Does that sound good?
sure, Professor, let's go with the session.
Okay.
That's fine.
So okay, great, great. So peace is back. Can I give the preference again? Whoever put it in the chat box, I'll deal with it later. I know a lot of you just jumped in, and I know group one is already there. I can't find preference for anything else. Group four is GANs, okay. So it's VGG net of birth. Group six is Gemini or DeepSeek. Group five is birth or group one is Wiki. Okay, group two, three, 7. I didn't get a preference. Group 2, 3, and 7. if you have a preference, please let me know. Otherwise, I can just assign something. Okay. GPT-3. Again, I can't guarantee this. Go to YOLO. Great. Group 3 and group 7, I don't yet have a preference. I haven't received a preference, so yeah, it looks like there's already no duplicates actually. So there was no need to panic, I think, from the start.
So I put the preference for 7 also on the chat.
Thank you. Yes, sorry. Okay, so it's only group 3 that's okay. So I think for group 3 alone, I'll randomly assign something, or you can give your preference now if that's okay.
You can assign, sir. Okay.
All right, sure. Thank you. Thank you.
Yeah, we can assign, no problem.
I'll upload this along with today's materials. Okay, the group and what has been assigned to you. If there are any corrections, please do let me know.
Okay, sounds great. Thank you.
Okay, group 2 and group 7, there's no need to get into a fist fight. We will figure something out. Okay, don't worry. All right. So that was the general idea with computer vision. Okay. Now, there are actually a lot of problems which even um, humans have difficulty processing, right? Like, for example, illusions. Okay. There's a famous illusion here. Is it a guy playing a trumpet or a lady, right, or a young lady? The question is there, and this is again what is this actually here? Can you see my screen? Am I audible?
Yes, yes.
Yeah, you're audible,
Yes.
sir. Just make a pattern,
Yes,
four
yes.
circles and a square. I don't know.
Okay.
It's a Pokemon character, right?
Okay. It's I mean, you're supposed to say it's a square, and then I say that it's just four Pac-Mans and there's no square there.
Yeah, Pac-Man.
Okay.
That's that's how the exchange is supposed to be.
Okay.
Anyway, yeah. So I guess this is a very famous illusion, right? I mean, the interesting part with this is in the brain there are actually neurons which fire when you actually see some edges, some sharp corners. Those neurons, they actually fire when you look at this image. Like the neurons which are responsible for processing edges and patterns, they actually fire when you look at these images. So but at the heart of it is just four Pac-Mans, right? So much so, we can actually see the line where it doesn't exist as well. Like we can imagine, and it's probably very real that we'll actually find like a thin line here between these two. So if things are going to be so complicated for the most evolved visual system, then think of how these things are going to be for a computer vision, right? What is this? This is a very non-traditional lighthouse, and this is I know it's a I know the guy looks old, but very famous movie star in India. So that's Rajnikant. But the idea is it's inverted, right? But we still don't have any difficulty identifying the intention. And I'm sure again I should probably make it more international. This is again the Indian Parliament, but the view from a top angle or something. I mean, the old Indian Parliament, the old building. The point here is we have never probably seen the building from this angle. We have seen bits and pieces of it from different angles in media coverage, in news, and in other in other situations. Um, but even when you look at this building from this top angle for the first time, will not have much difficulty identifying the building for what it is, right? Although we have not really seen this view, we have seen the view from multiple other different angles, and we know that it's a circular building, and based on our knowledge, right? Now these problems used to be really difficult for computer vision algorithms, right? Because it's a different context. You need labeled images. In a way, neural networks, the job is slightly, I wouldn't say simpler, but you can actually label this image like this is an illusion to the human eye, right? But as far as a neural network is concerned, this is probably a label, right? But the question is, what is the label that you will give to this image? Are you going to call it an illusion? You're going to say that, this is a young woman or a guy playing trumpet or a man. What is the label that you are going to give to this image, right? That becomes the real problem with computer vision, right? And some of the advanced models, like we discussed embeddings and transformers yesterday. So there are vision transformers which can actually understand more from the context and which can process this with a little bit more ease. But for traditional neural networks, the question is not really will the neural network be able to handle this? Of course, it will be able to handle this. The question is what label you need to give to this image in order for the network to learn, right? Are you going to call this an illusion? Are you going to call this a young lady or a trumpet or a man, right? What is the label? The last image is actually what is this actually? The last image here.
It's like a hand to me.
Yeah.
It's a yeah, it's a hand. Like, is it an impression or is it sticking out of the image or is it an impression?
Yeah, it appears 3D, so it appears three dimensional, so it's sticking out from the image. Is how it appears.
How many of you feel it is sticking out versus an impression, like stuck in? Like how um, you would see it if the impression of your hand is in a blanket or something, plush blanket. For how many it is sticking in, for how many of you it's sticking out?
Out.
Out for me.
Like it is coming out from the side.
Yeah, so it was a show from Titanic. Okay. Then what the show is, it's actually the impression on a plush blanket um, of my 2-year-old son. I mean, it was very realistic, so I captured the picture, but it really seems like it is sticking out, but it is actually an impression, right? So, I mean, it's the lighting and it is from which angle I'm taking the picture and all that. I know the internet went crazy over a couple of years back over the dress, right? Again, it was the lighting and the adaptive state of your mind and all that which helped in perceiving it. The point here being, for a neural network to learn or understand these things, first we need to understand what we want the neural network to learn, right? So what is the job of the neural network when you feed this image? Should it say that it's a plush blanket, or it should say that it is an hand, or it is an impression, or it is a 3D image? Like, what is it that you want the network to do if you send an image, right? If it is more than one thing, then that really was a problem until a couple of years back, until vision transformers came into the picture, which is going to be part of what we are going to discuss during the one of the variants as of deep learning. Okay. So the point I'm trying to make in this slide is you can train a neural network, but for that, we need to really understand what we want from the image. What is going to be the labeled data, right? Once we have that, it's possible to for the neural network to do its job. But for some situations, such as these, it's very difficult for even us to kind of figure out what we want from the neural network, right? If you want it to do like an illusion classification, illusion, not illusion, we give a couple of images which look like two images and which also doesn't look like two images, right? Like, how are you going to train the network, right? So all these things used to exist as computer vision problems until again vision transformers became popular. A lot of these things have become much easier, but it's still a challenge. Even nowadays. Okay, we discussed this slide yesterday. Common tasks with computer vision.
Professor, the slides are not moving. We still see that photograph.
Okay. Okay. I don't know what's what happened.
Yeah, now it's
Thank Slides are moving now.
yes, now yes.
Okay, thanks. Okay, so some of the real world use cases for computer vision. Okay, first we have what's called semantic segmentation, labeling a pixel with a class of objects. So as I said yesterday, a lot of even computer vision tasks are either of the two tasks, a classification task or a regression task. So I'll give some spoilers now. Usually I reserve these spoilers for when I do the correct job actually. But if I consider the segmentation task, we just do need to do a pixel level classification, right? For example, if there are three items here, one is a bone and one is lungs and the other one is heart. Okay. At every pixel, I need to identify which of these three classes the pixel belongs to, right? So at a pixel level, I'm doing a three-class classification, softmax, right? So that is the segmentation problem. And if I take this very complicated image, I have 3 or 4, 5 different classes of objects. A person, uppers, some plants or grass, and then there's a sidewalk and building. These are my 5 classes, right? Again, at every pixel level, I'm just doing a 5 class plot. Again, a softmax classifier, right? That's how we are going to solve a business problem or in any use case if it's a segmentation issue. Image classification is again, we are going to feed the whole image into a neural network, and we are going to let the network look at each pixel, and it's going to do something in the hidden layers, do some operation, and at the end of it, we are going to give some options. We are going to say, tell me if it's a pear or an orange or an apple or a plum or a lime or something, lemon. And that's just going to do a 5 class classification problem. Again, a softmax, right? Object detection. Object detection is finding an object of interest, putting it inside bounding box. That is object detection problem, right? In this particular example, it's humans that I am interested in. So the boxes are around humans. If I want to find open windows, then I would probably have boxes around here, and I don't know, probably around here. Uh, Probably that's all. I think there's a little open window here, right? So depending on what my task is, I'm going to get some sort of a bounding box. The detected object is going to be there. Again, this is one of the 2 problems, a classification or a regression problem. How is it one of these 2 problems? We can look at it 2 ways. For every pixel, we can see, I mean, we can do first a segmentation, right? And then we can see if this particular pixel belongs inside the box or outside the box, right? So we do a segmentation first. We'll study this when we do object detection, but I'm just giving an intro now. We do it segmentation, okay, and we somehow learn to mark the end of the segments, like mark this point. Okay, so this is my segmented image, and I just mark one end of it, and I mark the other end of it, and somehow I learn to draw a line here, a line here, a line here, and a line here. So that is basically my object detection task. This would become my bounding box. This would really become my bounding box, right? Now, again, I can just do a binary classification, and I can say if that particular pixel belongs to the bounding box region, or it doesn't belong to the bounding box region. That will just make sure that the box is ensured. The other way of looking at it is the image is basically here 512 by 512, let us say. Okay, let's say it's a 256 by 256 image. 256 rows. Two 56 rows and 256 columns, right? At the end of it, I should just find out if the bounding, I can convert it into a regression problem, and I can say, okay, from, what? Forget what I was saying. So 256 is a very bad number for uh, computer vision problems because the pixel level is also 256. So that will really make it difficult to explain. So let us say this is a 300 by 300 image, 300 rows and 300 columns. Okay. If I convert it into a regression problem, I just need to teach the algorithm to do a regression, to solve a regression problem where the minimum number is 0, the maximum number is 300, right? And it will basically, if it arrives at a number like 52.56, it will round it to 53, and it will say it is the 53rd row where the bounding box should start. Pretty efficient, right? And it will again do a regression problem to say the bound arrive at a number 144.26. If I round it down, it comes to 144. So 53rd pixel is the starting point for my bounding box. 144th pixel is the ending point for my bounding box. Similarly, I can do it for columns also, right? So I have converted the object detection problem into a regression problem. So at the heart of it, in computer vision, in almost all DLML, the data science problems, it is only either a text, a classification problem or a regression problem. And we can take both the approaches for the object detection task.
Professor, can you elaborate a little bit more for non-technical people? How would the linear regression come into the play here in terms of steps? Are you just
Okay. So I'll talk about it in detail when we do object detection. Okay.
okay?
But now the overall, you get the general picture, right? Somehow it is doing a regression, it is solving a regression problem where the minimum number is 0, maximum number is 300, corresponding to the number of rows here. Okay, let's say it arrives at some number 52.56 for finding the top part of the bounding box. It will just say the 53rd row, right, is the top part of the bounding box. That's all. How it does that is an object detection algorithm. We'll look at it when we actually do it. But I hope you can understand how it is become a regression problem now. Right? Okay. So object recognition is not just bounding box. You actually identify the item within that bounding box. So instead of just putting a box, it now says it's a dog, it's a bicycle, and it's a car. It really recognizes the object within your image. Now you might as well ask why it is not recognizing a window, or why it is not recognizing the shade, or why it's not recognizing the text, right? These boxes, they are completely task dependent. You have to tell the network why you are using this. What is the goal of using this particular model, right? This particular model which we have trained, it is trained to identify everyday objects like dog, bicycle, and car. If your algorithm is a specialized algorithm which actually identifies, windows, doorways, very architecture specific, building specific stuff, then it will put the box around those particular items and it will label them accordingly. Is that clear? The boxes and the labels are training dependent, model dependent. Is this going too fast?
Understood, Professor. Well, only thing is this basically it goes via the CNN filters, and then
Yeah.
we
We'll come to
join.
that. We'll come to that.
Yeah,
How
yeah.
this
But
happens
how
is
the
different.
yeah how the LR comes into that? That's something.
What is LR?
You mentioned about linear regression, right?
Oh, this.
Yeah.
Okay, okay. If you don't, I mean, I know I introduced this little early, but we will look at this in depth when we do object detection.
Sure, sure. Thanks.
Okay.
Prof.
Yeah.
Technically, for the object bounding boxes, we will need 2 points, right, in order to draw the box. So, for the earlier slide, where you were looking,
Minimum 2 points. Yes.
yeah. So for the
We-
earlier slide where you came up with the 50, yeah, this one, we need to look for 2 points, right?
Yes, that's
So we cannot
the
just
start
have
of
a
the
50.
yeah. So the start of the box, we actually need four, like the starting row, the ending row, the starting column, the ending column. We need
Yeah.
4 points.
So technically, if we are talking about a box, we just need the 2 diagonal points in order to determine the box. So essentially, the regression that we are trying to do is to identify the two so-called
Correct.
pixels in order
Exactly.
to
Correct.
define the box, right? Okay,
Exactly.
thanks.
Correct. Exactly. Yeah. Okay. Today there are a lot of applications for computer vision. We have reached a place where there are actually co-pilots and agents which are helping medical professionals diagnose diseases. It is actually marking, rather than just classifying an image, it is actually marking the place of a tumor, and it is doing some early warnings. Of course, these are um, uh, uh, um, working with the medical professionals rather than replacing them. And one of the so although computer vision can actually do a lot of things, one of the major business questions in the field is why has the adoption not scaled? Right? Year after year, I get in some form my DBA learners coming up with a project which looks into adoption rather than coming up with an algorithm or whatever. Okay. Well, a lot of many reasons are there. The point I'm trying to make is the algorithms have advanced, but there is still like a lot of gap in people trusting it, in people adopting it, and people using it freely in their everyday profession, right? Um, Surprisingly, one of the difficult and oldest parts of your computer vision is still OCR, which is optical character recognition. And this particular slide is at least, I would say, 8 years old. But I have not replaced this slide because the slide is still true. Okay. Because optical character recognition is a very diverse field actually. People can, if your text is clean enough, ChatGPT can do a very good job identifying these things. But as it gets more and more complicated, uh, the task becomes very resource consuming, right? And it becomes difficult even for advanced algorithms to do efficiently. Okay. So OCR has been one of the oldest computer vision problems, and it is still actually a problem. You can't really upload a document and just let the algorithm do a job. like this is a bill. What we really want is an Excel sheet at the other end or a JSON or something which says the name of the company, address, pin code, time, all these clearly sorted out, right? We are getting there, but not quite there yet. With that quick introduction, I think we will really jump into convolutions when we come back from the break. So let's take a 7-8 minute break and come back. Okay, let's start. Okay. Great. I'm going to use less slides and more talking and discussion. Okay. Now, let us say I have an image and I have a like a plain white noise kind of a thing, or no, a plain white part, and actually an image of a mountain. Okay, how do I know that there is something in an image?
By comparing with the known templates.
Okay.
Ultimately, which means that we will start detecting from detecting the edges and corners, and then finally sum it up to some template, known template, and then we will try to identify the parts or components of the image and maybe try to aggregate that what it totally sums up to.
Okay. I fully agree with your definition. So I guess what my question was, how do I know that there is something in this image and there is nothing in this image? Both are black and white pixels, right? Both have different levels of gray in them. What makes this image recognizable? Niaz's answer was little, I would say, algorithmic. Okay. But we'll just do some free thinking and see how we can, what makes this image, what makes us say something, that what makes us say that there's something in this image. Let's start there. The first thing that we would say is there's nothing in this image, and there is some object in this image. What is it that makes us say that there is something in this image and there is nothing in this image?
There's some difference across the pixels.
There are clusters of pixels where 1 minute, Niyaz, I'll come to you. Give me 1 minute. Rio, where are the clusters of pixels? In the left one or in the right one?
In the right one, so there are patches
The
of
right one.
white and there are patches of black and there are patches of gray.
Okay, yeah, great. So there are clusters of pixels. Great. What was Niyaz's answer? I didn't catch that. What was that?
There are variations, and again, those variations have some relations, so we infer that. So first of all,
Okay.
primarily the variation.
Okay. So I think both the answers pretty much they are the same thing. So there are clusters of pixels, and the other answer was there are variations. Okay. One thing I would want to add here is there are systematic variations. Okay. Even in the in the left image, there are variations, right? But it's not systematic. And thus those systematic variations form the clusters, right? So there are these white patches, right? And it is very clearly demarcated from its surrounding. There are these black patches, which again is clearly demarcated from its surrounding, which is this. Okay. So one of the basic features of an image, okay, is this differentiation between foreground and background, which is defined by what are called the edges. Okay. Those systematic variations and the clusters, they are defined by this particular shape. Yes. And here probably there is another thing going on here. How will I know that there are two peaks? Because there is one peak here and there is another peak over here. Right? So people started with computer vision and then they said, hey, look at this image on the left. It is just random pixels. Okay. Look at the image on the right. The same pixel values, but there is a systematic variation. And people thought, okay, if there is a way to actually identify this systematic variation, I will find out what is the shape contained in the image. And if I get the shape, I can find the object, right? Because it is the shape which, after all, defines an object, right? If I have to draw a face, I would start with two eyes and then a nose and then a mouth, right? Each of this is a shape, right? This is a curve shape, this is some shape, right? So if I can come up with different algorithms which can actually identify the shapes, then I can identify what the object is. That is the basic assumption in my computer vision approach. That's the basic approach to computer vision problems. Yeah? Is that clear?
Yes.
Now, if I have that, the next immediate step would be how can I really find what is there in an image? Okay. And we can do a small exercise here. Give me a few minutes. I'm opening an Excel sheet. Why do I see and S the color of my saying the wrong button? Okay. Okay. Um, Okay. So for a long time, people working in computer vision, they thought that if I can come up with a method to identify a shape in an image, I can solve any problem in computer vision. For example, if I have to identify a face, the defining characteristics of a face are two eyes which are separated by a particular distance, the presence of a nose and a mouth. Okay, if this basic structure is there, then I can identify a face. So people came up with ways to create a shape. Like for example, they would come up with a particular mathematical equation which would define this particular shape, right? Once that happens, they would actually search for the shape inside the whole image, inside a given image. Okay. If it matches, then it gets some 5 points or 10 points or something. Okay. And then they would come up with another equation which would identify something that identifies a shape which is like this, like one curve above and one curve below. Again, they would look for this shape in the whole image. Okay. And if there's a match, they would give some score to it. Right? This is how people approached computer vision problem for a long time. Now, the thing that I said, where you create an equation which will identify the shape, right? That process is a very old and very established one in physics called convolution. So convolution is basically there is a signal. One moment. Okay, so convolution is basically when we have some unknown signal. We want to find if a particular pattern is present in the signal or not. Right? So one way of looking at it is we look for the pattern. If let us say this is the pattern I'm looking, this is my signal and I don't know what it is and all that. Okay. I want to see if this particular pattern is present inside the signal. So what I would do is I would come up with an equation which will define this shape and I would pass it through different aspects of this unknown signal, and if there's a match, I will get a different score. So if this is the signal I want to find, and this is my unknown my unknown signal, I would pass this thing which I'm going to call the function, okay, or the kernel or the filter, okay, the kernel or the function or the filter. I would pass it through the signal, okay, and if there's a match, it will give me a high score. If there is no match, it will give me a low score. So if this shape is not present in the signal, I'm going to get a 0. let's say I have another signal which goes something like this. Right? Now, if I pass this kernel through this signal 2, this is signal 1, so signal 2. If I pass this kernel through this, okay, it will search for this particular shape within this signal, like in this segment, in this segment, in this segment, in this segment, like in different segments, it's going to look for this. And if there's a match, for example, it will find a match here because these two shapes are nearly similar, right? So it will give me a score. It will give me a score like a strong score when it passes through this segments of my signal, right? When the kernel or the filter passes through different portions of my unknown signal, if it finds a match, it's going to give me a strong score. If it does not find a match, it's going to give me a weak score. This is the basis for convolution. This is the basis for 1D convolution, which has existed in physics for quite a long time. The mathematics is also surprisingly simple. It is just a dot product. Okay, so mathematically, what we are trying to do here is I'm doing a sum product. As you can see the Excel sheet here, right? The same signal and the same function. I'm doing a sum product. If I double click on this, sum product of A1 to G1 versus A2 to G2. This is my unknown signal. This is my known function. I created these set of numbers because this is the signal I want to search. This is the function that I want to search within this particular unknown signal. Okay, so what I will do, I will pass this kernel through the whole signal, right? So here, I'm passing it through this, I'm getting some score. If you see here, I've moved it by one step, right? And I'm repeating the process. Here, I've moved it by another step and I'm repeating the process. Here again, I'm moved it by one step and I'm repeating the process. So what I'm looking for is some positive value, and then the value comes down, it goes up, comes little bit down, stays like that for some time. This is the variation in the numbers that I'm looking for. And if you look at the signal, okay, when the score is high, it is exactly the way that I'm looking for, right? The signal starts high and then it comes down and then it goes high and it kind of stays at a particular level. That's why I'm getting a good match at this position. Did you get this concept? Did you get the concept of convolution? I'm defining a filter or a kernel or a function, and I am passing it through an unknown signal, and I'm looking for the same pattern within that unknown signal. Here the pattern being start high, go low, again start high, remain in the mid. That is the pattern, that is the shape that I am looking for. Right? Where there is a high match, you can see that's exactly how the signal is. Starts high, comes low, goes high again, stays somewhere in the middle. These numbers. Right? This process is called convolution. The known function through which I am searching for a particular pattern is called a kernel. Okay? the place where I am searching for a particular function is called my signal, or not my unknown signal. Did you get the concept of convolution? If the pattern is present, I will get a high score. If the pattern is not present, I'll get a very low score. As you can see here, the pattern that I'm actually looking for, again, start high, go low, go high, remain in the mid. But if I look at this part of the signal, there's hardly any variation, right? It starts, I mean, it's somewhere in the mid and just remains there. That's why I'm getting a weak match. The value is just 0.98. Here, this part of the signal, it is actually the exact pattern that I'm looking for. 2.76, 1.3, 3.03. This is 1.5, but this is 0.7, but that's okay. 1.4 and 0.06. Right? This part completely agrees with this part. That's why I'm getting a high match here. That's why I'm getting a big number here, which shows that this particular pattern is present in this part of my unknown signal. Let's forget images, let's forget everything else. Did you understand this concept? This is 1D convolution. Any questions here?
Professor, I have a question. Again, I'll ask it from a non-technical perspective. So yesterday we were discussing cat sat on the mat, and then when we feed enough data, it figures out that what cat does.
Yeah.
It seems like similar principle is involved here, right? We are feeding it tons of data and it's figuring out on its own that what should be the next step.
So we haven't gone into the neural networks part of it. We haven't even started dealing with images. I'm just explaining the process of what is convolution.
Okay. All right.
Okay. So convolution as an operation. This is what it is. Okay. I am looking for a particular pattern in an unknown signal. Why am I looking for the pattern? Because I feel that finding the pattern is crucial to solving a problem. Like if you take the images, for example, if I find a curve like how I described in the slides, if I find a curve like this, it's not right anywhere. So
Professor.
Yeah.
Oh dear, hold on.
I think that's a little better. All right. Could you just highlight the formula? Just put your cursor on the spreadsheet so I can see the formula, just to understand the numbers.
Yeah.
Oh.
Okay. So at the heart of the mathematical operation is basically, if you click here, A1 times A2, this is B1 times B2, C1 times C2, D1 times D2, E1 times E2, up until here. And I'm summing it. That's what this number is. Okay?
Yeah.
As I said before, it is looking for the pattern in different points in my unknown signal. So it looks at the first segment and then it moves to the second segment to find if it is present there or not. So that's why I have moved the thing to this part of my signal, right? And again, I'm doing the same thing. P1 times P2, C1 times C2, and I am summing it until I reach here where these numbers match exactly with my known function that I'm sending into it. Okay, 1 minute, I'm getting a problem. I'm sorry. Now, telemarketers have become very smart. I think they are using agents to make these calls. So previously, if I pick up a call and if I don't answer, it will get disconnected automatically. Now it is almost like a conversation. It waits till I say hello, and it starts talking. And if I interfere, it stops and all that. I think they are implementing AI agents faster than us. At the speed in which we are teaching it. Anyway, so that is 1D convolution. Is the operation clear?
So, yeah, this is clear, Professor. We just want to understand. So, you are calling it as 1D. Is it because this is single dimension and it is going to become
Yeah, correct.
multi-dimensional? Okay.
It is going to
Okay.
become, yes. It's going to become
Okay.
slightly more complicated.
Okay. This is clear.
Okay.
Thank you.
You can use convolution to perform a lot of things in an image. Okay. I'm not going to go into this because this will eat up a lot of time. Let us say that I have an image. I am going to. Okay. Let us say I have an image like this. Okay. These are the pixel values. This is a 5 by 5 image. Okay. These are dark portions of the image. You can see slightly gray parts of my image. This is a really bright pixel. This is a really dark pixel. This is somewhere in the mid. And these are really bright portions of my image, right? If I'm going to color code the okay, this is my image number 1. Then I have my second image, which is like this. Okay, these are the pixel values in image number 2. Okay. Now, remember, we started out with the assumption that a meaningful image always has identifiable features. One of the basic identifiable features, as you guys pointed out, is these clusters of pixels, which is separated from the background. Okay. So one of the basic tasks that people came up with is something called edge detection. So they would go to an image and they would really sit and try to find where is the edge which separates an object of interest from the background. Okay, so one of the earliest problems that people try to solve in computer vision is this thing called edge detection. Okay, so the assumption being if I'm able to detect the edge correctly, I can somehow figure out the shape of the edge and I can find what the particular shape is. Like for example, in the TensorFlow playground that we saw, we had one vertical line and one horizontal line, and we were somehow able to come up with diagonal lines based on by transforming these two these two filters. That was the assumption. All this is before neural networks came into the picture. Okay, so people were trying to find the edges, right? of an image. And they started using the concept in physics, and then they thought, okay, my image is the signal. Okay. If I can come up with a mathematical equation which will if I'm able to come up with a mathematical equation which will basically define a particular shape for me, I can use that as my kernel or filter. I can send it to my signal, which is my image, and basically find the shape. Okay. So to that effect, one of the basic things that you can actually do is come up with an edge filter. Okay. The purpose of the edge filter is to look for a transition from a dark part of the image to a bright part of the image, or vice versa. And why this is important? Because that is exactly how you can see my entire screen, right? Because that is exactly how a real image is going to be. Now, at the end of the day, what makes this part different from this part? It is the surrounding. The surroundings have different overall grayness level or brightness level, and this has a different brightness level. Okay. And this has a different brightness level. This has a different brightness level. So people set out to actually define a shape, and then they thought, okay, one of the basic things I want to do with an image is find the place where the pixels go from bright to dark or dark to bright. Okay, that is the basic for my edge filtering. Is that clear? Now, this filter is very easy to define because all this filter needs to be is uh, something like 255, 255, 255. Okay, 255, 255, 255, and have values such as 0, 0, and 0. Okay, why did I define this number? Because I want to find the parts of the image which basically go from bright to dark. So I defined a kernel which is basically bright to dark. And now I'm going to convolve this kernel through my unknown image. Is that clear? Is the objective clear here?
Yeah.
Okay. Okay, so I'm going to send this. I'm going to send this image, send this kernel through my filter. Still not sure why it's not sure. It's demo. It's been a while since I used this. Any one of it. I'm not getting the result that I usually get from this.
We lost your screen, Professor.
I know I'm trying to fix something.
Okay,
Usually
okay. Yeah, yeah.
I get a very dramatic change of numbers. I don't know what I'm doing differently this time. I'm not able to see the necessary effect that I want.
Okay, thank you,
Yes,
thank you. Yeah.
I got it here. I think I got it. Okay. I think I didn't define the kernel properly. Now it's better. Okay. So as you can see here, this is the kernel that I want, which closely matches the shape that I am searching inside the image. Okay. And I have two images where the numbers are, pretty random, I think. And a second set of numbers where there is a systematic variation. Okay. So I'm going to have 140, 255, 455. Now all these numbers are there. So I am actually sending this kernel inside this image. Now, instead of being 1D convolution, this has now become 2D convolution because I'm using a two-dimensional kernel on a two-dimensional image. So the operation is still the same. It's going to be 1 times 27 plus 0 times 42 plus 0 times 24 plus 1 times 140 plus 0 times this, 0 times this, 1 times this, 0 times this, 0 times this. Okay. So if you look at the operation, I am basically trying to do a sum product, like a dot product of this kernel through this signal, right? And I'm doing it for the entirety of the image. I'm just sliding it across the whole image. I'm looking for this particular pattern first here, and then here, and then here. And since I've run out of space, I'm moving down, looking for it here, here, here. I've run out of space, so I'm looking for it here, in this part, and in this part. Okay, that's how these numbers are. This is the same convolution that we did for 1D signal, but this time it is a 2D signal. The kernel is two-dimensional, the image is also two-dimensional. Is this part clear? Convolution as an operation. Okay, it's very quiet today for some reason.
I have a question.
Don't worry about the numbers for now. Okay, just how we translated the 1D convolution to a 2D convolution. At this point, it's enough. You don't have to understand anything about neural networks, how the training is happening, nothing. We are talking about pre-neural network time when people are still doing these things manually. At this point, the only knowledge is, there is a kernel, and if I can define the correct kernel, I can pass the kernel through an entire image, and I can search for that particular pattern within the image. The assumption being, mathematicians, statisticians, physics people, they will all come up with an equation to define a shape, like a curve or a circle or a semicircle or whatever. Okay, mathematicians will come up with a way to come up with an equation which will define a shape. I will, as data scientist, send that shape using 2D convolution into an image, and I will find if that particular shape is present in the image or not. This is where we are currently. Don't worry about neural networks or anything. Are we good till here?
Everything is good, Professor. Only one trivial question. It's
Yeah.
technically a correlation, not a convolution, right?
Uh, it is convolution as an operation because this is the convolution part of it.
So it's x of n and y of t minus n. That will be the convolution, right? Now here, what we are doing is technically a dot product. So that will be a correlation, right? So if I'm doing a sigma I equal to 1 to capital N, x of n dot y of n, then it will be technically a correlation, right? So I always have this question because in the DSP terms, the correlation is taking a template of a signal and trying to get a dot product.
Yeah, correct.
And whereas convolution is basically inverting the template and passing through and getting it.
Yeah, correct. Technically, yes, correct. I agree with that. Yes.
So it is fundamentally a misnomer, but it is being adopted by everyone. Is it correct?
Exactly. Correct. Correct. So if you want to talk in terms of pure digital signal processing, you are correct. Convolution involves the inversion operation, which we conveniently ignore here.
Thanks, Professor. Thank you.
Yes, correct. Okay, so till now, I mean, if you didn't understand, others do not understand that conversation, that's completely fine. It's been, I think, more than 10, 15, 10, 12 years since I opened a book on digital signal processing. It was the last time, I think, in my PhD days, before my PhD days, that I read about these things. So, yeah. But that's okay.
I have a,
Yeah.
so I have a question
So,
with regards to the previous Excel sheet that you had shown.
the
When you
current
were
Excel
explaining
sheet.
the previous one where you were explaining some product, but you can explain it from any sheet. It's not really specific to,
Okay.
it's not sheet specific. When you were
Okay.
explaining some product and effectively you looked at the signal and then you looked at the function and you arrived at the sum product, there was one number at the end, which I assume is the score, right? What does that
Yeah.
inform us?
That is the strength of, that's what we are coming to. Yes.
Okay,
That
got
is
it.
that is the number which basically says if the number is high, you can think of the pattern being present in my unknown signal.
Got it. So
If the number
5
is
is
low,
the
then this
cutoff.
pattern I'm looking for is not there.
Got it. And will the number always be within a particular range of 0 to 10 or something like that?
We can scale it up, but it really depends on what numbers are originally being fed into it. So we can
Correct.
always range the values between 0 and 1, or we can truncate the numbers. Yeah.
Got it.
I have a question, Professor. So here, like when we decide the kernels, okay, so we decided kernels as 0 and 1. Is it fixed that we have to decide between 0 and 1, or we can also take like 0 and 10,
Yeah.
or 0 or 100, or 0
Yeah.
to
So
55?
yeah. So those numbers, I'll come to those numbers. Those numbers are basically defined by would come from an equation typically, right? Like an edge detector is actually an algorithm. So
Okay,
people will come up with an equation and they will actually give us those exact numbers.
okay, got it.
Yeah, so there's a whole field in that's why computer vision used to be an interdisciplinary thing where physicists, mathematicians, statisticians, people come together to solve a computer vision problem more than a data science problem.
Yeah. Okay, got it. Thank you. Yeah.
Okay. So I did the dot product, and here I'm basically any number that's less than 0, I'm scaling it to 0. Any number that's more than 255, I am making it 255. So as you can see here, this is the output of my convolution. Okay. Now what the kernel has passed through my signal and it has given me this output. And you can see that if I'm going to convert this into an image, I'm going to have a plain white image. There are going to be no features, right? This is going to be a plain white canvas because all the values are 255. There's 191 here, but that won't make any difference. No identifiable shape. Whereas if I pass this kernel through my second image, okay, which actually has this pattern in it, okay, which actually has this pattern of bright to dark and dark to bright, I am getting a meaningful shape as an output. As you can see here, all these numbers are 109, 127, and these numbers will fall in the gray part, and all these will be white, right? So what this kernel has done is it has found out the parts in an image where this pattern is present. How will I know that? I am getting an output which is very similar to my kernel instead of just noise. If the pattern is not present in my image, I just get noise or a very plain white or a very dark, canvas. But if this pattern is present in my image, I will have something that is similar to my kernel. Okay, white to zero, dark to white, white to dark. I'm getting that pattern here. Okay. And as I can see, if I pass this kernel, through here, again, I'm getting some meaningful representation. These would be gray and this would be a very white region. So I would actually get the shape that I am looking for. A transition from dark to bright or bright to dark. Okay. So convolution as an operation helps me identify a particular shape in an existing image. Is that clear? Why did I do an edge detection? Because I thought that edges are the very basic features which are present in an image. And I'm using the word feature here the same way I use feature in traditional ML. Right? So convolution as an operation, if I want to do, let us say, right Sobel is basically an edge filter. So you can see the filter here, -1, -2, -1, 0, 0, 1. So this basically there are the numbers change from negative to positive, right? And this is actually a very real filter. Somebody asked about the numbers which go into the filter, right? So this is actually this is a right Sobel filter, which basically does edge detection from left to right. If I convolve an image using this is what I would get. This identifies all the areas in the image where there's a transition from a dark area to a bright area. If I change the filter to top Sobel, you can see how it identifies all the horizontal brightness variations. If I change this to left Sobel, this identifies transitions from bright to dark areas. 1 to 1 to -1, -2, -1. Okay. Again, if I do a bottom Sobel, it identifies transition, brightness transition from dark to bright. All I need to do is slide the particular, as you follow the red color dot here. All I need to do is slide that kernel over my existing image, right? I do this and then I come down, do it in the second row, and then for the third row, and then for the fourth row until I'm done with the whole image. So convolution as an operation helps me identify, look for a particular pattern within an image. Did you get this part? No answers? I will briefly explain. I'll continue explaining it, but for now, do you understand how convolution picks up patterns from images? If you understand that much, I think we can move on to the next section.
So it's like it's translating to the computer language.
Yeah.
That's what I understand. And it can depicts the patterns and it's like normalization, right?
Yeah.
Yeah, like it normalize like a bit, but then like normalize the whole picture into one language. That's what.
Yeah. Basically, yeah. Okay. So once people have a way to come up with a filter to look for a pattern, that's when the real model building starts. Okay. So they would come up with something called a right Sobel score, a left Sobel score, or a top edge score. Okay. I'm just giving an example. Okay. Or if you want to find some complicated pattern, like the curve of the eyebrow or something, okay, they would, I mean, people who actually come up with the numbers which go into the filter, right? They will sit for hours, months, and your whole PhD will be spent in finding one particular shape of an image. Let us say I want to find out, or I know I want to identify a cat. Okay, so let's say this is my cat image, and I hope it looks like cat. Okay, so what really makes me identify a cat? It is the ears, probably the whiskers, the eyes, the nose, and all that, right? So in an imaginary situation, a lot of people from a lot of discipline will come and they will spend like months, years of research identifying the earness. And how can you find that? What the ear is basically a shape, right? So it is one diagonal line like this and another diagonal line like this. So which is basically some order transformation of my right Sobel score and my left Sobel score. Because the right Sobel score gives me one line, left Sobel score gives me another line, like transition from bright to dark. Left gives me transition from dark to bright, right? So if I'm able to combine these two, I will come up with one single line, right? And my top edge score will give me another line. In some order transformation of these two, I can come up with a diagonal which actually correlates with this diagonal. Some transformation of that will give me an edge where these two lines meet, right? So these are engineered features, like how we did x squared log x PCA, we did feature engineering, right? So people actually did these feature engineering. for any object identification. And they would come up with some sort of a score or some sort of an zero, present, not present kind of a thing. So let us say somebody has found a way to detect whiskers. So it will be whiskers present or absent. 0 for present, 1 for absent. 0 for present, 1 for absent, like this. And probably a nose score. I'm just making it up, okay? So 0.9, 0.6, 0.3, etc. So this will be cat image 1, cat image 2, cat image 3, right? So they will come up with an algorithm which will do this, and then they will train it on a set of cat images. Okay, and then they will build a model like a classification model. Okay, cat, not cat. Calculate the error, right? And then update the model, and this is exactly how ML, traditional ML, was used to solve computer vision problems. We haven't gone into neural networks yet. You see how convolution as an operation helped in solving computer vision problems. So people would actually come up with equations which will find a particular shape. They would engineer features from that, do whatever, first order, second order, nth order transformation for that, and then come up with some score for that, feed that into an ML model, do random forest SVM or do something with that, and come up with the animal, cat or dog or, whatever score. Instead of ears, instead of whisker, I can even call it distance between nose. Distance between eyes. They come up with a metric and hope that this extra feature will increase the accuracy of my model by 3% or 2% or 5% or whatever. Is it clear till now?
Yes.
Okay.
Yeah.
So parallelly, what's happening is neural networks are slowly becoming a thing. Okay. People are starting to use neural networks okay, which is now capable of handling humongous amount of data, right? But as far as computer vision is concerned, people still don't see the point of neural networks because still people are dealing with computer vision as if it is a structured data problem, right? They are engineering features, they are doing something with the data. At the max, what they can do is they can send these, the edge filter scores and have some hidden layers and hope that the neural network will somehow figure out the nth order transformation, which will basically find which will finally detect the correct pattern within that image, right? That is the maximum they can hope for. But even that, it quickly overfits and the manual extraction of features doesn't work with computer vision. So parallelly, neural networks are becoming a thing. And what's happening is people are asking a new question where they say, okay, the power of neural network is basically to um, engineer these features, right? We don't have to give the features and let the neural network learn. So parallelly, people are saying, no, don't worry about the feature extraction. Forget it. Just send the whole image into the neural network. When I say whole image, if I take a 228 by 28 pixel image, all the 784 features, all the 784 pixels are now individual features. So one feature is one number. Okay. In the first approach, where I used convolution to solve a computer vision problem, my feature was the result of my convolution score, my filter, my kernel, whatever I was using. Right? Here, the feature is the pixel value itself. Right? That people are trying to send into the neural network, and they say, I'm not going to, if I have to, let's say, identify a number 8. Okay? I have to identify a number 8. I have to really, this is a very complicated number, right? So I have to come up with feature which will find a curve, which will find another curve, and which will also define how this curve sits on top of another circle, right? So one circle on top of another circle is basically my number 8. So I have to come up with an equation which will detect this, which will detect one circle sitting on top of another circle, if that is my thought process, right? So people who are doing neural networks, they say, okay, dump it. Don't worry about doing the feature extraction manually. Send the whole image, all the 784 pixels. For a 28 by 28 image, there are 784 pixels. Send all the 784 pixel values as input features. Let the hidden layer figure it out. Okay, this is happening parallelly when the manual feature extraction is also happening. Okay, and this surprisingly gave very good results actually. Okay, so just with such a simple network, densely connected, the same classic good old ANNs that we used, we get some reasonable accuracy of around 80-85%. Okay, and I can do it on my laptop. I don't need any complicated compute for this. Now, even in the 80s, it was fairly doable. Even in the 90s, it was fairly doable. So, on the one hand, people are solving computer vision problem using convolutions. And on the other hand, people are trying to solve computer vision using ANNs. Okay. The real power of convolutional neural networks came when people started combining the convolution operation into the neural network, right? Now, if you look at the image, the Excel sheet that I actually showed, there was a very nice question that came. Who decides these numbers, right? In the example that I actually showed using the kernel filter, okay, in this, can you see the screen with the filter?
Yes.
Okay. In this filter, the numbers are 1, 0, minus 1, 2, 0, minus 2, 1, 0, minus 1. But the numbers that I used here, okay, 1, 0, 0, 0, I can actually change this to minus 1, minus 1, minus 1, and I will still get reliable results here. Right? The same pattern. So now who decides what number goes into the filter? Right? That is what CNN basically solved. Okay? So in CNN, what people did was they combined the power of convolution, which is capable of finding patterns, with the power of ANNs, which is basically the promise of today, of that day. Okay. And people basically said, I'm not going to define these numbers. I'm going to let the neural network figure out these numbers by using what it's good at. Weight, random weight initialization, back propagation, weight updation. So instead of the humans giving the kernel values, people said, I am going to modify my artificial neural network, my ANN, in such a way that I'm going to pass filters and I'm going to convolve that filter over my image, but I'm not going to give the actual numbers for the kernel. I'm going to let the neural network figure out those numbers. So in a CNN, basically, these numbers are randomly initiated. Okay, they are randomly initiated. As the network trains, okay, it learns which feature detection is important. Now you see, I am giving the filter. I'm telling that in my Excel sheet, I was telling the catness score, the distance between the nose, how two lines join to become the edge. All these things I was actually defining, right? Now, if I have one, two, three, or multiple hidden layers, in the first initial layer, probably some diagonal line is going to be figured out, right? In the second hidden layer, how those two lines are combining to form a shape is going to be figured out. And in some other hidden layer, how two shapes are combined to form a more complicated shape is going to be figured out. That is the intuition behind using CNNs for computer vision, right? So the crux of it is the correct numbers in my kernel. Once I come up with some kernel size, 5 by 5, 10 by 10, 20 by 20, some kernel size, and I give some random numbers as weight initialization, the network, after training, will figure out that, for this particular image, it is this number which is optimum. Right? This is still doing the job for me. But along with it, you see, it is doing something else as well. This number, which is neither the number that I manually gave, nor the right Sobel filter, which is a well-established filter. Okay? But it is actually finding the edge in two places where probably it was not present using the previous filters. Why? Because the network learned these numbers. I did not give these numbers. Okay, that is the intuition behind using convolution inside a neural network so that we have the power of convolutions, but we also have the learning capacity of the neural networks. Combine these two, and what we get is convolutional neural networks. Any questions? Or was that too much to take in today?
No, I have a quick question. So I totally understand the concept, like combination between convo and the CNN, but it seems to me like it's backward, like back propagation to come up with the numbers, and so it seems like you I don't know. So how do you like the output is from the kernel? You get it from by timing with the kernel function, but then the kernel function is optimized by the output. So so it's like the kernel function you get it in the first place by experience, right? Or it's like the eggs and the chicken. I think I wonder if it makes sense.
Yeah. So when you do it manually, that's what is happening. But the thing with neural network is it becomes really simple. We will see in the next class how none of it really none of your physics knowledge or your kernel knowledge really plays a role in um, in identifying a particular feature.
So it's like if it's manual, it will be tired, but if it's like automatically, it like test and trial for like hundreds and thousands of times that it will
If
come
it's
up with the
manual.
right one. It goes back and
Correct,
forth, back and
exactly.
forth.
Back and forth.
Thank
Yes,
you.
correct. So the weights keep updating and it comes up with a filter value that is specific to this problem.
Got it. Thank you.
So, sir, when PC comes into picture, when we're defining that what feature is having a maximum weight to define the
What
actual
comes into the picture? PC.
PC, principal component analysis.
Oh, yeah, we are done with that. We are done with PC. So once we enter neural networks, we are assuming that those types of feature engineering, the network will take care of it.
Okay, perfect.
Sorry, what did he mention again? PC?
PCA, principal component analysis.
Oh, okay. Thank you. Thank you, Vince.
Okay. So once we have this concept cleared, it's a smooth ride from now on. We are just going to discuss. We are just going to correlate combine the operation of convolution with the power of neural networks in the way it updates weights and combine together and see how it solves a particular problem. That will be the focus of next class, and it will be really fast from here.
It's very interesting, Professor, the concept today, and I was just trying to think of a real example in our workplace of how this is working. And we use a piece of software in our vehicles. And one of the key risks that we have with 3,000 commercial vehicles and 3,000 drivers is distracted driving. And we use a piece of software that recognizes when a driver picks up a cell phone. So it recognizes the device, and then combining that convolution with other aspects, it determines that the driver is distracted and issues an audible alarm that they're distracted. And so in real, like just applying what you've put here today, the fact that they used edge filtering to identify a handheld device and then putting it into the neural network. And as I'm just reading a little bit more, there's trillions of data points that it's running against for all of these different aspects to determine that this is actually a device and learning from it, learning from the driver and the behavior. So that's a real example that's in our current workplace, right?
We'll do something. We will take this example and build on this example in the next class. Like what data would be required, what might be happening inside the network, and all that.
For sure.
That will be
And
really
one other
interesting.
comment, when I looked at your picture of the mountain and the black and white, again, and this is where the human part comes in, I saw the same thing actually. Both of them are granite. One is a finished product and one is the actual raw product. And so again, having that reference, one is a slab of granite that's finished, one is the raw product, right? So anyway, I thought I'd share that with you too.
Yeah, sure. Yeah, it's interesting.
Thank you.
Okay, so there are no other questions. I think we can end the session. Thanks everyone for the attention.
Thanks, Professor.
Thank you
Thank you very much.
Thank you very much.
Thank you.
Thank you. Thank you very much.
Thank you.
Thank you.
Okay.